So I just want to make this probably going to be a long video about ordinary differential equations because it's troubling some of my students. And I'm just here to basically break it down into bite-sized pieces and just to let you know that it's not that hard. When you're working with ordinary differential equations, by the way, this is within the context of A2 further maths core 2. So FP2. When you're working with ordinary differential equations, there's really two or three main things that you're being tested on. Number one is you're being tested on your ability to integrate. So, can you integrate? Number two, you're being tested on your ability to separate out variables. So, can you rearrange and separate variables? And then I guess the third thing is you are being tested on your ability to spot patterns and basically simplify equations. So can you spot patterns and simplify equations? Okay. Now, as we go through some very basic examples to explain some of the core concepts of ordinary differential equations, these 3 points will make a lot more sense. If you remember back in core maths, so C2, C3, C4, integration was basically its own discipline of mathematics, especially with trigonometric functions. You had to use so many mathematical techniques in order to integrate things. And this is no different in ordinary differential equations. We are going to have to draw upon our earlier core knowledge in order to, integrate some of these expressions. But you'll find that with practice, what looks very complicated becomes very trivial. Can you rearrange and separate variables? Well, this is to do with just finding solutions. Solutions of expressions is basically y equals, or z equals, or x equals. All you're doing is you get given an expression and you're trying to rearrange and separate variables such that the end result is y equals some function of x. Or if they use different letters, z equals some function of another letter. And then this is closely linked with point 3, where in point 3, one of your main goals is to, so I'm going to jump the gun here. One of your main goals is to figure out whether you're looking at an exact differential or an exact derivative. And especially if it's a trigonometric function, you can simplify it into something that's easier to work with. Yep. So in first order differential equations, separating variables and basically do you know how to integrate is as simple as this particular example here. So example number 1. So we get given an expression that says dy by dx equals y over 2x x plus 1. Okay. Now, I remember seeing this a lot in C4, where one of the last modules, especially after parametric equations, was differential equations. Ordinary differential equations is basically one step after that. So the first thing we're going to do is that we are going to get the variables on the side of the differential and then go from there. Okay. So I'm going to dress this up by dividing both sides by y and multiplying both sides by dx, such that we get our updated expression as so. Okay, now I'm actually going to take this 2 and just pull it over there. I don't really want to deal with this 2 in the midst of all these x's. So I'm gonna get my my lasso and just exit that. Get my lasso over here, just exit that out of there and put the 2 right on top of there. Okay, that looks easier to work with. So this should now be pretty straightforward, especially on the left side. On the left side, I basically got 2 over y. This is a standard integral. When you've got a variable to the power of 1 underneath some constant, you just raise it to the natural logarithm. So that becomes 2 ln y on the left hand side. On the right hand side, however, this again, this looks to me like C4 stuff. Do you remember partial fractions? Because I don't know about you. Oh, by the way, these are integrals. I don't know about you, but I can't integrate this just off the top of my head. I mean, I don't think anyone can. We need to dress this up a little bit. We need to change this into something that's easier for us to work with. Okay. So that means using partial fractions. So the right hand side is currently this. And the way we dress up partial fractions is to have a constant divided by one part of the variable minus another constant divided by the other variable or function rather. So this is its own equation, or this is its own expression. Okay, so I can multiply both sides by x bracket x plus 1 to get me 1 equals a x plus 1 and b minus b x. Okay, now I'm trying to find out what these coefficients are, so I can get these coefficients by setting x such that the other coefficient should be eliminated. So I would say when x equals minus 1, the coefficient a goes to 0 and I'm just left with b. So 1 equals minus b times minus 1. Therefore, b equals 1. Likewise, in order to get rid of the b, when x equals 0, I get 1 equals a. Well, 0 plus 1, so a equals 1. Okay? So a equals 1 and b equals 1. And just so that I don't waste space here, I'm going to take that over there. A equals 1 and b equals 1. So that means this expression here, or rather this expression here, the integral, actually becomes 1 over x minus 1 over x plus 1 dx. And these are very easy to integrate. So the right hand side now becomes ln x minus ln x plus 1. And you must remember that you would actually use substitution for this one. But because the substitution, u equals x plus 1, when you differentiate that, you just get 1. You get no constant, or you get 1 on the outside, which doesn't need to show up. Okay? So this is the right-hand side. So therefore, our total integral is going to be 2 ln y. So therefore, 2 ln y equals ln x minus ln x plus 1 plus some integration constant c. Now this isn't the final solution, because the final solution is something based upon y. So y is equal to some function of x. So what I'm going to do is that I'm going to raise y to the power. I'm going to get rid of this 2 and raise y to the power. Then I'm going to exponentialize everything so that I get rid of this ln. So that's going to be y squared equals oops, I can't even delete that. That's going to be y squared equals, I'm going to put these together first of all. So that's going to be ln x over x plus 1. And then I'm basically just raising this to the power of e. And I'm also raising c to the e. Or I'm raising e to the power of c, sorry. These cancel. Actually, that multiplies with this. So I get y squared equals x plus 1, and then I get the c there. Okay. Sorry for the hesitation. I just wanted to be sure that I was doing things correctly. I don't have notes. So this is going to be my exact solution, where c is some constant. Okay. Example 2 basically talks about exact differentials or exact derivatives. Exact derivatives. Now, exact derivatives are you just have to be able to spot them. You really just have to be able to spot them. So an easy example is, I have an expression of sine x dy by dx plus y cos x equals 3x squared. Now, the trick here is to find where dy by dx is and just squash it with whatever it's next to. So I'm looking very closely at this expression on the left-hand side. If I was to modify it slightly, I would have d over dx y sine x, and then plus y cos x equals 3x squared. If you actually went ahead and did this using product rule, so let's actually just go ahead and do that using product rule. So product rule, back in C3, you have two functions, and you name one u, you name the other v, and you're basically following this expression here. The differential of two functions of x, where one of these functions is actually y, is going to equal to v du plus u dv. So if my u is y, then dy by dx is just going to be dy by dx, and then multiplied by v, so that's just going to be sine x right there, plus u, which is y, and then dv is simply cos x. This happens to be equal to this whole thing here. That is what you call an exact derivative. And that is what helps you simplify these expressions so easily. So this whole thing, this whole sine x dy by dx plus y cos x can be reduced to dx y sine x. So actually, my expression is now uh, my expression is now d by dx y sine x equals 3x squared. And like in example one, all we're doing is just rearranging variables and making something the solution, so that making something the making something the main guy. I'm sorry, my terms elude me right now. Making this the subject, so making y the subject so that you can calculate the solution. So let's rearrange everything. In fact, we don't even need to rearrange anything. We have a dx here. What we can do is that we can multiply both sides by dx to get y sine x equals 3x squared dx. Now, because we're integrating, that just becomes an integral. Okay? And we don't touch this. We actually do not touch this, because that's connected directly to the y. We integrate this, so we get y sine x equals x cubed plus c, and then we simply divide both sides by sine x to get the solution. So y equals x cubed sine x plus c over sine x, and that is the solution to that particular example. So here, example 2 was an example of when you should look for exact derivatives. I don't know why this thing keeps popping up. And example 1 was just an example of rearranging the variables, making something the subject of another, and using methods from earlier core modules to help you integrate. The third example talks about something very, very it's just process, it's just convention. So example 3 is just integrating factors, or integration factors. So the diagram of that is IF. Integrating factors, you don't have to think of anything, or you don't have to think deep about it, except that you must turn your expression into the form of dy dx plus py equals q. Okay, and the caveat is that p and q must be functions of x. So if you rearrange it to the fact that you've got dy over dx plus some function of x equals some function of x, make sure it basically looks like this. Yep, make sure it looks like this. And then the integration factor is, you will now take p and you will just turn it into this. Don't ask me why it works, it just works. I've never bothered to look too far into it. Not everything in maths you need to understand to the letter, to be honest, as bad as it may be for me to say that. But this is a method which is just following a convention, and you take p, you put it in an exponential, and you integrate it with respect to dx, because it should be a function of x. you get out a new value. Half the time, the integration of p will be a natural logarithm, so that the exponential can cancel out the natural logarithm, and then you would then multiply everything by this whole thing here once you've integrated it. So in essence, that expression there becomes e p dx plus dy by dx plus e p dx times py equals e, again, p dx times q. Okay, so let's have a look at a quick solution, or rather a quick example. So we have x dy by dx plus 2y equals 1. In order to get it into this form here, I need to rearrange the expression and basically get this by itself. So I divide both sides by x, and I get 2y over x equals 1 over x. 2 divided by x is a function of x. So my integrating factor p is actually 2 over x. So this means that I can integrate that with respect to dx, and that's going to give me e to 2 ln x. Now I'm going to take this 2 up, get rid of it, to give me x squared, and these two should cancel. So I get x squared. I'm going to take this and multiply everything by x squared now. So I'm going to get left with dy by dx x squared. I don't know why I keep putting an equals there. I'm just too used to dy by dx equaling something. Plus 2xy equals x. Okay. Then the next thing I'm going to do is that I'm going to again take a close look at what's going on here. Take a close look at what's going on there. These questions are very predictable. Take a close look at what's going on there and realize that this is an exact derivative, because dy by dx y x squared, again I'm going to put my u and I'm going to put my v and follow the convention v du plus u dv. So v is x squared and du is just dy by dx. U is y and dv is 2x. And as you can see here, this whole thing is the same as this. So this whole thing equals that. So I can simplify the left-hand side. So simplify left-hand side to get d by dx y x squared equals x. Now I'm going to multiply. Now this here is its own little function. You shouldn't touch that. So multiply both sides by dx to get y x squared equals x dx, and I'm integrating. Integrate as so. Divide both sides by x squared, and this is our final Solution. Okay. So I just want to recap quickly. Ordinary differential equations is focusing on, do you know how to integrate? Do you know how to rearrange and separate variables? And can you spot patterns and simplify equations? Spotting patterns and simplifying equations is everything to do with exact derivatives and using the integration factor. So rearranging well, I guess number two is more about rearranging in order to get the integration factor. And then can you integrate if you've got something over x, or if you've got trigonometric functions, do you know how to integrate them? In the next example, or in the next video rather, I'm going to go through two common exam style questions based upon ordinary differential equations that you will almost definitely be tasked with solving. And you will find out that once you just bear in mind all these three, it's literally just, can you integrate, can you rearrange and separate variables, can you spot patterns and simplify equations? Not necessarily in that order, but you will find out that just bearing these 3 points in mind will help get you through the questions.